All right, so let's go on page 28. On Friday, I front-loaded you with some things to kind of go back and knock some cobwebs off of imaginary numbers and maybe some things that you really hadn't heard before, but you were expected to have heard before. I don't know. But I think the last thing on your notes was the conjugate root theorem. And I only gave you kind of half of it because I didn't think we needed the other half, and then I was wrong about that. So this is the conjugate root theorem continued. And we are going to fill it in from the bottom to the top because the bottom is what we already talked about. So we talked about what the conjugate root theorem said. We were talked about it with imaginary numbers, that if you had one imaginary root, you had to have two because they come in pairs, right? So that's what we're going to start by filling this in. This is also, but we'll get back to the other part. If a plus bi is a zero of the function, then a minus bi is also a zero. So 2 plus 3i, then 2 minus 3i is also 1. You don't even have to have the 2 part. If I just have 2i, then negative 2i is also 1 because they come in pairs. Okay, that makes sense? That works the same way for irrational numbers. So we have a polynomial with rational coefficients. Then the irrational roots occur in conjugate pairs again. So if I have a plus the square root of b, then I have to have a minus the square root of b. So that could be like 2 plus the square root of 3. Then I'd also have 2 minus the square root of 3. Or if I have the square root of 5, I have to also have negative square root of 5. That's because when we multiply them back together, we get the whole number that we want. Okay? So both the imaginaries and the square roots, they come in pairs. Okay? Just an important little tidbit there. All right, so now let's talk about symmetry. Symmetry is part of, this is part of Algebra 2, okay? At least pre-AP Algebra 2, I know it's definitely part of it. We talk about even and odd functions. So the terms even and odd describe the symmetry that exists for the graph of the function. Now, an even and odd degree is different than an even and odd function, okay? So if the degree of my function is 5, it's a 5th degree polynomial, that's the degree. It could also be an odd function, but we don't know. So the degree being odd and the function being odd, two different things, all right? Not guaranteed that they always go hand in hand. So let's look at these. So a function is even. We'll write even out here so it's bigger because I didn't have room for my labels. Function is even if and only if you have the point x, y, then the point negative x, negative y is also on the graph. Okay? So for every point x, y, you have a negative x, y. Think about what that means. If I have a point x, y, it's over here in the first quadrant, let's say, then negative x, y, that negative x, it would end up over here, right? The even is just a reflection in the y-axis. A function is odd if and only if, so we'll put odd over here so we can see it bigger. When you have x, y, you have negative x, negative y. You change the signs on both. So for the even, you're just changing the sign on x. For the odd, you're changing the signs on both. In addition to that, for the odd functions, every single time f of 0 is equal to 0. So every time in an odd function, if x is 0, y is 0. So what that tells you is that for an odd function, it always passes through the origin. Okay? 0, 0 is always a point on an odd function. Remember, odd function and odd degree, not always the same thing. Okay? And then this is how we're going to look at it algebraically. We're going to look at a couple of things before we actually get to that, but we'll talk about what that means here in just a minute. Okay? So let's look at these examples. It says determine whether each graph is even, odd, or neither. And I'll kind of leave those up there. So if I look at this point right here and this point right here. So I have, this point is at negative 1, 2. This point is at 1, negative 2. Right? And then really the first thing you want to check is what is f of 0? What is f of 0 for this? 0. Now, that does not guarantee that it's odd, but it opens the door to where we could possibly have an odd function. All right, so that's not a guarantee. It's not the only thing we have to check. But we checked that. So then when I have this, now would you agree that this function looks like it's symmetric in some way, right? This negative 1, 2, do I change the sign on both of these or just one of them to get this point? Both of them. Because this, and it goes to the origin right there, which means that this is an odd function. And then we would say it's odd because for every point xy, there is a point. And every time I put a point, it looks like I'm abbreviating apartment because with this stupid board, my stuff slurs together. That doesn't mean apartment. It means a point. Okay? There is a point, and then since it's odd, it's negative x, negative y. On the key to the assignment, I'm pretty sure I also put that it passes through the origin. You don't have to put that, and we don't have room, so we're not going to. But I'm just telling you that because I'm pretty sure I wrote that on the key, and I'm not going to go change it. So if you put it, great. If you don't, it's not the end of the world. Okay, we good on that? Questions? All right, let's look at B. What is f of 0 here? What's f of 0? 4. Okay, which tells me it's not odd. Does not guarantee that it's even. It's either even or neither, but it's definitely not odd. Okay, so then when I look at the points here, I'm going to pick these 2 points. Now, those points aren't even on whole numbers. Okay, they're not even that nice. But this point, whatever it is I can't even tell on my graph. It's negative x, negative y. Would you agree with that? Then this corresponding point over here has the same values except for the signs, right? This one is x, negative y, because we know what happens in quadrants 3 and 4, right? So if that's happening, all we did was change the sign on x. Ooh, now it looks like it's negative. We changed the sign on x. That's what's happening over here, which means that this function is even. And I can say for every xy, there is a point negative xy. Okay. And I didn't put the same signs that are on the graph because that's not what the rule says. We okay with that? Any questions? All right. Now this, well, we'll come back and talk about the symmetry. Let's look at C. What is f of 0? 0. Which means it could be odd, not necessarily odd, right? Do you see any 2 points that you could pick where you could either get negative x, negative y, or just negative xy? No, right? Doesn't happen at all. And so this one is going to be neither. We can say for every xy, there is not a point negative x, negative y, or negative x, y. What questions you got? Anything that makes sense? Now, when you look at them graphically, you just look at these 3 graphs. This one just looks way different than the other 2 do, right? Not that the other 2 look alike, but when you look at them, there's some sort of symmetry, some sort of similarities throughout the graph where this one just seems kind of random, right? So if a function is even, every even function, not just every function with an even degree, but the function itself being even. So notice this one is even. We have a line of symmetry right there. Is that the x-axis or the y-axis? That is the y-axis. So an even function is symmetric with respect to the y-axis. It has line symmetry or reflection symmetry. Okay? A function is odd. So this one, I can't reflect it like I can in B, right? But there's a reason it has to go through the origin, because it has what's called origin symmetry. right? Which you first learn in geometry, then you talk about it with odd functions in algebra 2. But it has rotational symmetry of 180 degrees. I cannot rotate my board, but if you turned your paper upside down, wouldn't the graph of A look exactly the same? Okay, if that happens, it has rotational symmetry, or has what we call origin symmetry. So a function is odd if it's symmetric with respect to the origin. Okay, we good? Odd is origin symmetry, even is y-axis symmetry. If we have x-axis symmetry, then we're not a function, so we don't really worry about it. Okay, we good? Now we're going to look at algebraically. So we looked at it graphically. Now we're going to look at it algebraically, which means we're going back up to do these two things right here. We have to find f of negative x. If f of negative x equals f of x, it's even. If f of negative x equals negative f of x, then it's odd. Okay? So here's how this looks. We're going to find, so this is my function. So I'm going to find f of negative x. Means I'm going to substitute in a negative x. So we get negative x squared plus negative x minus 12. Now, if you can already figure out what it is without doing this, nobody cares. Okay? Your work is part of your answer. So you can't just look at it and say, oh, I know what's going to happen. That's great. Nobody cares. You have to write it down. That is your proof of what you're doing. Okay? So then I get f of negative x equals, what's negative x squared? X squared. Okay? Then that would be minus x minus 12. Okay? So I substituted it in, then I cleaned it up a little bit. After I've cleaned it up, then I compare this with the original one. Do those look identical? No, they do not. So that means f of negative x does not equal f of x. My only other option is, does it equal negative f of x? So in order to figure that out, I have to factor out a negative, which would leave me with negative x squared plus x plus 12. Okay? So then I compare what's inside these parentheses to this. Do these two things look identical? No, because this is negative x squared and that's x squared, right? So it didn't equal x squared. It doesn't equal negative x squared. So this one is neither, because neither one of those match. And I regret starting with a neither, because I think it would make more sense if we had done like a different one first, but that'll make more sense after we do B, I think. Gail, you with us? Yes, I'm sorry. Did I do it wrong? We're here. I squared this and I got positive, then this is plus a negative x, so that's minus x, and then minus 12, is that what you're asking? This one? So I factored out a negative, which makes this negative, which makes both of these positive, because I got to change the sign, right? Did I do that right? Okay. We good? Makes sense now? Okay. So this doesn't, what's in here doesn't match that exactly either. Okay. We good? This stays the same. I got my equation the whole time. This right here on the right-hand side, all of these are f of negative x, because I substituted in the negative x, right? And then I want to compare it. Here, hold on to that question. I know where you're confused. And again, I wish I had done B before I did A. So let's do B, and then I'm going to come back to your question. Okay? I'm not putting you off. I think that it might make more sense if we do B, and I think it might answer your question within that. But I'll come back to it. All right, let's look at B. F of negative x. This is equal to negative x to the 5th minus 4 times negative x cubed. Okay, I substituted in my negative x, yes? Okay, keeping my equation the whole time so I don't have random stuff all over the place. So I have f of negative x equals, now negative x to the 5th, is this going to be positive or negative? Negative, so that's negative x to the 5th. And then negative x cubed, this part's negative, and then it's times a negative 4, so that becomes plus 4x cubed. Okay? So I've substituted in, I've cleaned it up. As it looks right now, what's on the right-hand side, does this match this exactly? No. So then I'm going to do f of negative x and I'm going to factor out the negative. So my left is still the same just because I substituted a negative x. This is x to the 5th minus 4x cubed. So now does what's in my parentheses equal this exactly? Yes. So this is f of x, right? So that means that here what I have is f of negative x equals, I'm bringing down that negative, and then this is f of x. So f of negative x equals negative f of x. That's what I have shown in my work. That's why my work has to make sense and can't just be random all over the place. And because f of negative x equals negative f of x, what is this, even or odd? Odd. Okay. And this, guys, this is your explanation. There's no words because that is proving what you just did. Does that help answer your question? Of what or ask me again if it didn't. You good? Are you sure? Anything else? Okay. All right, let's do C. So f of negative x, this is what I'm testing, is equal to 2 times negative x to the 4th. Oh, that's a 5. Negative x to the 4th minus 6 times negative x squared. All right. So I substituted in, that's my first step. Then I clean it up. I don't do them all in one step. So negative x to the 4th, is that positive or negative? Positive. So that's 2x to the 4th. And then negative x squared is positive. So that's minus 6x. Yes? All right. So, oh, thank you. So now that I've done that correctly, does this match this exactly? Yes, that means that, so I'm bringing this down right here, f of negative x equals, and then this is f of x. And since f of negative x equals f of x, this is what? Even. What questions you got? We all good? We sure? See why I should have done B before A. That's a regret, but too late now. All right, we good? Okay, so let's look at example 3. It says determine the symmetry, if any, that the graph of the equation will exhibit. So without me graphing it and looking at the symmetry, the only other way I can do it is algebraically. So this is f of x. So I got to figure out if it's even or odd. So again, I'm going to do f of negative x. That's going to give me 9 times negative x minus negative x cubed. That step is important. You have to show that you substituted it in, not that just magic happened and you wrote other stuff down. Okay, so then f of negative x, when I clean it up, I get negative 9x plus x cubed. Everybody with me at this point? Does this match my original exactly? No. So that means now I factor out a negative. This is still f of negative x. This gives me negative then 9x minus x cubed. Now, does what's in here match my original exactly? Yes. So that means that f of negative x equals negative f of x, and that does make it odd. But I still have to write both of these things and all of this, like all of that is my answer. But that's not what this question was asking, right? It was asking me for the symmetry. So the symmetry, then, okay, and we're going to put this little, you know what these little three, oh, you know what these 3 dots mean? Therefore, exactly. This is the abbreviation for therefore. Therefore is a long word, but we can use the little 3 dots instead. That's how you write proofs, okay? So I can say therefore, and this should have been called f of x. Therefore, f is symmetric, and we can abbreviate symmetric with SYMM, symmetric with, W with the slash, respect to, and that wording may sound weird, but that's how you say it, symmetric with respect to what, if it's odd? The origin. Okay. What questions you got? Are we good? Just kind of tying those two pieces together. All right, flip it over. Okay, using differences to determine degree. So we've sort of already done this. We've done it a little bit. We did it just to determine if our function was linear or quadratic, but we can determine more than that. So this is taking it just a little bit farther. So the degree of the polynomial function can be found by examining the successive differences to the output values over equal interval input values, right? Not a brand new concept because, like I said, we've already kind of been doing that. The degree of the polynomial function is equal to the least value for n for which the successive nth differences are constant. So what this is telling me is that we know if the first differences are constant, it's linear. If the second differences are constant, it's quadratic. So if the third differences are constant, it's cubic. If the fourth differences are constant, it's quartic, and so forth and so on. Okay, you can just keep on going. So we're just extending that a little bit. What I didn't leave you enough room for on this example, because I was trying to make this just on one piece of paper, was to actually check this equal interval input values. That is super important, and some of y'all weren't checking those things on your quizzes, and you didn't have a clue what you were doing here. But I can, so 2 minus a negative 3, this is between here and here, this is 1. 1 minus a negative 2, that's 1. 0 minus a negative 1, 1. So all of these, they're all 1. Okay, so since they are equal length, they don't have to be 1, but they have to be equal length. If they were all 2, that'd be fine too. But you got to check that, okay? Then the other thing is, some of you got lucky on some of those answers, or you were totally wrong. Either you got lucky or you were totally wrong because you can't add and subtract positive and negative integers. That's a huge problem. So when I do this, negative 14 minus a negative 30 is 16. Negative 12 minus a negative 14, 2. Negative 12 minus a negative 12, 0. Negative 2 minus a negative 12, 10. 30 minus a negative 2, 32. 96 minus 30, 66. Okay, so this right here, these are my first differences. They are not constant, therefore I know it's not linear, right? I can't just say what it's not, though. I've got to say what it is. So then I do it again. 2 minus 16, negative 14. 0 minus 2, negative 2. 10 minus 0, 10. 32 minus 10, 22. 66 minus 32, 34. Make sure I'm right on all of those. Okay, so these are our second differences. Not constant, not a quadratic, right? So then I do it again. And notice I'm doing it on all of them. I'm not doing it on some of them and then making a conjecture. I'm doing it on all of them. 2 minus a negative, no, I'm sorry, negative 2 minus a negative 14, 12. 10 minus a negative 2, 12. 22 minus 10, 12. 34 minus 22, 12. These are our third differences. Okay? Third differences are constant, so the degree of my function is 3. Now, this really should be named, and it's not, so this says y. We're going to call it f so that we have a function to call it, because we need to make sure we name it. So then we can use our fancy therefore. Therefore, f is a third degree, and it is fine to say cubic, but I'm assuming you probably don't know all the names past that. Third degree or cubic polynomial because, and b/c is fine for because, we can abbreviate that too, because third differences of f are constant. Notice what we didn't say. We didn't say anything about the average rate of change. It's not the average rate of change of the third differences, and it's not the third difference of the average rate of change. Those of you that are connecting those things together, that is not correct. You either talk about differences or you talk about average rates of change. They are connected, but not in the way you're connecting them. And we'll get to how they're connected eventually. Okay? Everybody okay with all that? Any questions? All right. So let's look at example 5 real quick. Actually, we'll just stop here. This is where you're going to start tomorrow. So you don't have to tape this in.